Alright, so now we're going to go on to banked curves, and although all you can do is really just memorize the equation to find the bank angle of the curve, of the curve, I'm going to show you guys how to do it, just because I think it really shows how you can mix in Newton's second law with radial acceleration and with normal acceleration. So here I've already drawn the force diagrams for the curve, so we're going to assume that this is a car, this dot. I tried drawing a car, but it was really bad. So we're going to have our force gravity acting directly downwards, our force normal, which is going to act perpendicular to our plane, or our curve, or banked curve in this case. So now if you use some trigonometry, here's a 90-degree angle, so this would be 90 minus theta, and since this is parallel, you know that this is theta, and in the end you get that this angle is theta. So we want to first do our Newton's second law as always. So we know that the summation in the forces in the, or radial force, let's do radial force first, is equal to Fn sine theta. Since that is the only force that is acting towards or opposite to the center of the circle. And now we can set that equal to our radial acceleration, which we know as mv squared over r. And we're going to now also look at our forces in the y. However, you must keep in mind that in the y, it is no longer acting towards the center or away from the center of the circle. Therefore, you cannot set it equal to mass times radial acceleration. We could only do that for Fn sine theta since it is acting towards the center of the circle. See, this is a bank that goes around in a circle. So acting up and down, it's no longer acting towards the center of the circle, so our summation of the forces in the y is just going to be equal to Fn cosine theta minus mg, which is going to be equal to 0, since we're not accelerating upwards. And so now let's solve in terms of force normal, and we'd get mg over cosine theta. And now we can substitute in for our original equation. So we have our summation of the force radial is equal to Fn sine theta. We're going to plug in mg over cosine theta for Fn, and then we have to keep the sine theta is equal to mv squared over r. Now we can eliminate the masses since they are on both sides of the equation, and we can reduce sine theta over cosine theta, simplify that as tangent theta. So we have tangent theta, or g tangent theta, is equal to v squared over r. And you should know from trigonometry that sine theta over cosine theta is tangent theta, and cosine theta over sine theta is cotangent theta. So now we have our equation, tan theta equals v squared over rg. So now let's look at the question. Find the angle at which the bank requires no friction. And in this example, we had no friction playing, so this would be the equation of a bank having no friction. And don't worry about a question that would ask you with friction. That is not at this level. So we're really going to stick with these not simple but not very complex problems. So just remember, for a banked curve with no friction, tan theta equals v squared over rg, and save yourself some trouble. So now we can just write theta is equal to tan inverse v squared over rg. And our radius is given as 50 meters and our velocity at 50 kilometers an hour. So we can write that as theta equals tan inverse v squared would be 50 divided by 3.6. So you get 13.89 meters per second squared over 50 times 9.81. And whenever you're going from kilometers per hour to meters per second, a really easy tip and a helpful tip is just divide by 3.6. You could do it using stoichiometry, but you'll see that since you're multiplying by 3,600 to get seconds and divided by 1,000, 3,600 divided by 1,000 is 3.6. So just divide 50 by 3.6 and you get meters per second. So you would get an answer of 37.5 degrees. Theta is equal to 37.5 degrees. There. So that's how you would find the bank angle for a banked curve without friction. That's a key point. So lastly and not leastly, as we say in my country, Newton's universal gravitation in geosynchronous satellites.